Welcome to Linear Programming and Applications. Today we are diving into one of the most fascinating and powerful concepts in optimization, primal-dual relationships. Imagine every problem you solve has a hidden mirror image, revealing secrets about your resources that the original problem hides. By the end of this video, you will not only understand how to find this mirror image, but you will also see why it is absolutely essential for solving massive real-world problems and extracting deep economic insights. Let us get started. To understand what primal and dual mean, imagine you run a bakery. Your main goal is to maximize your total profit by deciding how many cakes and loaves of bread to bake with your limited flour and sugar. This original, direct problem is what we call the primal problem. Now, imagine a competitor wants to buy your entire bakery operation. They want to minimize the total price they pay you, but they must offer at least as much money as you would have made baking. This competitor's perspective is the dual problem. In linear programming, every single optimization problem has this hidden mirror image problem attached to it. Now that we understand the bakery analogy, let us look at the mathematics. We first write down the standard form of a primal maximization problem. Conceptually, this formula calculates our total profit by multiplying the profit from each item by the quantity produced, while ensuring we do not use more resources than we have. In this formula, Z represents the total profit in dollars. The vector C represents the profit contribution per unit, and X is the quantity of each product we decide to make. The matrix A represents how much of a specific resource is consumed, and the vector B represents the maximum available resources, like the total kilograms of flour. If the available resources in vector B increase, we loosen the constraint, allowing our production X to potentially grow larger, which increases our total profit Z. This mathematical setup leads us directly to the mirror image dual problem. Conceptually, the competitor wants to assign a value to each of our resources to minimize the total amount they have to pay us, while ensuring the offer is fair. Here, W represents the total valuation of all resources in dollars. The vector B is the exact same vector of available resources from the primal problem. The new vector Y represents the dual variables, which act as the price assigned to one unit of each resource. The matrix A transpose ensures that the implied value of the raw materials inside a product is greater than or equal to the original profit C. If the original profit C increases, the competitor is forced to increase the resource prices Y to satisfy this inequality, which in turn increases the total valuation W. Before we move on to a concrete example, let us visualize these transformations. What you're seeing here is the core mapping between the primal and dual problems. Notice how the objective coefficients of the primal, the vector C, cross over to become the right-hand side constants of the dual constraints. Conversely, the right-hand side constants of the primal, the vector B, cross over to become the objective coefficients of the dual. The constraint matrix A is transposed, meaning its rows become columns and its columns become rows. Finally, observe how the maximization problem flips into a minimization problem, and the less than or equal to constraints flip into greater than or equal to constraints. This crisscross pattern is the mechanical heart of primal dual relationships. Now that we have seen the mapping rules, let us apply them to a basic numerical example. We are given a primal problem, where we want to maximize an objective function based on two variables, subject to two constraints. Our strategy is to extract the mathematical components first and then apply the mapping rules to build the dual. We start by identifying the profit vector C, which holds the coefficients 3 and 5 from the primal objective function. Next, we identify the resource vector B, holding the constants 4 and 6 from the right-hand side of the constraints. Finally, we extract the constraint matrix A from the coefficients of the variables in the primal constraints. With our components extracted, we can now construct the mirror image. Since the primal was a maximization problem, the dual will be a minimization problem. We use the resource vector b as our new coefficients to write the dual objective function, which we want to minimize. Next, we construct the dual constraints by transposing the matrix A and using the profit vector C as the new right-hand side. The first column of the original matrix gives us the coefficients for the first dual constraint, set greater than or equal to 3. The second column gives us the second constraint, set greater than or equal to 5. We use greater than or equal to because the original primal variables were non-negative. We are now ready to finalize our dual problem. Because the original primal constraints were less than or equal to inequalities in a maximization problem, the rules dictate that the new dual variables must be non-negative. We have successfully converted the problem. The final dual problem is to minimize W equals 4y1 plus 6y2 subject to our two new constraints, with both variables being non-negative. Physically, this mirror image contains the exact same fundamental information as the original problem, just viewed from the perspective of resource valuation rather than profit generation. The standard form is clean, but this brings us to an important question. What happens when a problem does not perfectly fit the standard form? Sometimes a linear programming problem might have a mix of different inequality signs, or it might have an unrestricted variable. An unrestricted variable is allowed to be positive, negative, or zero. In these cases, we must pay careful attention to the relationship rules for mixed signs. The sign of a constraint in the primal strictly dictates the sign of the corresponding variable in the dual. Conversely, the sign restrictions on the primal variables dictate the type of constraints in the dual. Let us see how this works. Let us convert a minimization primal problem with mixed constraints. We are given an objective to minimize z subject to a greater than or equal to constraint and a less than or equal to constraint. Notice that the first variable is non-negative, but the second variable is unrestricted in sign. Because the primal is a minimization problem, the dual will be a maximization problem. Let us determine the signs of the dual variables first. In a minimization primal, a greater than or equal to constraint is considered standard, so the corresponding dual variable y1 is non-negative. However, the less than or equal to constraint is non-standard, which forces the corresponding dual variable y2 to be non-positive. Now we formulate the dual objective function using the right-hand side constants of the primal constraints, which are 5 and 8. We want to maximize this dual objective function W. Next, we construct the dual constraints. The type of constraint in the dual is dictated by the sign restrictions on the primal variables. The first primal variable x1 is a standard non-negative variable, so the corresponding first dual constraint takes the standard less than or equal to form for a maximization problem. The second primal variable x2, however, is unrestricted. A strict mathematical consequence of this relationship is that an unrestricted primal variable forces the corresponding dual constraint to be a strict equality. Applying the rule for the unrestricted variable, we write the second dual constraint as a strict equality, using the coefficients from the second column of the primal constraints. This completes our conversion. The final dual problem is to maximize W equals 5y1 plus 8y2 subject to our two new constraints, with y1 being non-negative and y2 being non-positive. Physically, this shows that even when a problem has messy, mixed constraints, the strict mathematical rules of primal dual relationships allow us to perfectly translate every single condition into its mirror image without losing any information. Now that we have used these formulas, let us understand why these relationships matter in the real world. Sometimes a company faces a primal problem with millions of constraints, but only a few variables. Solving such a massive system directly takes an enormous amount of computer processing time. By converting it to the dual problem, the millions of constraints become variables, and the number of constraints drops to just a few, allowing computers to solve it much faster. Furthermore, the dual variables have immense economic value. They are often called shadow prices. A shadow price tells a business exactly how much their total profit would increase if they could get one more unit of a scarce resource. We have covered the full topic of primal dual relationships. Let us reinforce the most important ideas. First, the primal and dual are two sides of the exact same mathematical coin. Every variable in one corresponds to a constraint in the other. Second, the objective coefficients and constraint limits crisscross between the two problems, while the constraint matrix is transposed. Finally, mastering these relationships is not just a mathematical exercise. It gives us the ability to solve complex optimization problems faster and extracts deep economic insights like shadow prices about the true value of our limited resources. You now have a solid understanding of this powerful optimization tool.